Hi, my name is Sophie Witowski, and this is my Lab 4 Oscillations video report. To start off, the purpose of this lab was to observe the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. After we observed this unique motion, we would then track our data using Tracker and compare the predicted motion and observed motion of the mass. We will also find the estimated period of oscillation in both the x and y axis and demonstrate whether the energy principle is satisfied. As a preview of the results, the predictive model will be an overestimate of the observed position because the computational model is an ideal system with no energy losses, meaning it does not account for air resistance or any other external forces. We also determined that in the computational model, the sum of energies will be equal to 0 because it is an idealized system. Before we get into the experiment, we must talk about the physics fundamentals used in this lab. We used Newton's second law, spring mass relations, and the energy principle to help us achieve our goal. Newton's second law is m times delta v over delta t. The force of the spring is equal to k times s. Period is equal to t equals 2 pi times square root of m over k. S equals the length of the spring minus the relaxed length of the string. K energy is equal to 1 over 2 mass times velocity to the second. Potential gravity equals mass times gravity times distance. Potential spring energy equals 1 over 2 k times s to the second. Now that we have that out of the way, we can begin to analyze our video. In my experiment, I chose to use the video provided to us in Lab 4 instructions. Using other informational videos, it was found that the initial conditions were m equals 0.402 kg, calibration length was 0.7 meters, time between frames was 10.5 seconds, and the frame rate was 0.095. We also found the physical characteristics of the system to be K of the spring equals 6.87 and relaxed length equals 0.126. The initial position was negative 0.117 in the x-axis and negative 0.632 in the y-axis and 0 in the z-axis. Our delta t was 9.497 seconds. Our system is the spring, mass hanging from the spring, and the earth. Our surroundings would be the physical objects around the system, but these have no effect on the system, so they equal 0. Next, after analyzing the video and tracker, we move on to our computational model. In the starter code, we had to edit these lines, input initial conditions, formulas for the energy components, calculate net force, update the velocity, position, and spring, and calculate energy changes. You can see the edits and changes I made in the images if you would like to pause the video. To finish the computational model, we needed to insert a .csv file for the program, and to get this, we first copy and paste the position data using the x and y coordinates from the tracker into Google Sheets. Then we export a .csv and upload that into GlowScript. As a result, we get these two images. On the left, you can see the spring mass movement, and on the right, you can see the relation between all of the energies. Using this information from our data, we can now analyze the predicted model's position versus the observed experiment position. It was found that the model overestimated the position. This is because it is an ideal system that does not account for air resistance, internal friction in the spring, and any other possible outside forces at play. It was also found that the computational mass moves further from the origin than the experiment, around a 0.01 to 0.02 meter difference in the y-axis and an even smaller distance in the x-axis. It was also found that the experiment oscillates at a faster period than the predicted model. Some possible sources of error include a tracker error. Perhaps I didn't correctly align my calibration stick. I might have not also chosen the correct center of mass in every frame. The camera angle could have thrown something off. Air resistance and an initial velocity might not be 0 due to the person dropping the mass might have accidentally added some initial force. What does this mean? For the first question, for your model system, is the energy principle satisfied? The answer is yes. The energy principle is satisfied because the summations of all the energies in the system equals 0. This means the energy is conserved. For the second question, using the data you obtain in Tracker and make two separate estimates of oscillation periods, first by estimating the period of oscillation from the x position data, and second by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. It was found that the y position time averaged out to be 1.5193 repeating, and the x position averaged out to be 1.646. Because the periods of oscillation were relatively close to each other, this indicates the graph of oscillation is relatively accurate. If we take an estimate of the period in the x and y, the true period of oscillation would be around 1.6 seconds. That's all at the end.